this video, I want to talk about the special types of linear systems that you have already learned how to use the three methods for solving linear systems, which are graphing, substitution, and elimination. So if you don't know how to use those three methods, I would go back and look at an earlier video, and then you can look ahead to this one. The idea is that for my students so far in this chapter, we've always worked out problems that had one solution, and that solution was a point, x comma y, where our two equations basically want to think, now that we're talking about other cases, about what other possibilities are there. So our first possibility is the one we've already seen, where if our graph has two lines and they intersect, and let me just attempt to make it be nowhere near a nice point. Here, we'll pretend it went through this point. Look, we've got one solution, 2, 3. So that is one situation that we have, is that our lines intersect, and we can find the point where they intersect either by graphing or by working it out using substitution or elimination, but it gives us one solution. That is our normal case. If you think about what other cases there are then, if we're implying that, we don't always have lines that intersect, well, what kind of lines don't intersect? It would be parallel lines. So let me see if I can do a better job of drawing this time. Let's say that this is one of our lines, and so we might have another like this, and so it looks like there's an equal distance apart this whole way. And so what we do is we call these parallel lines. Parallel is a word that means that they will never meet. If you think about what is required to make parallel lines happen, you may have noticed because of the way I drew it, we have to go up and over the same amount in order for them to be parallel, which means that they have the same slope. But an important distinction is that they did not have the same y-intercept. So they had the same slope, which is how we knew they were parallel lines. What we're going to call this, whenever this happens, is that there is no solution to a problem like this. Because if our solution to our system is where they intersect and they don't intersect, then there can't be a solution at all. The third case that we have is kind of weird whenever we talk about it, because what happens with this third case is either algebraically or through graphing, what ends up happening is we draw our line and then we draw the same line right on top. So here I've got my red line that's happening, but I've got another equation perhaps that I would just end up drawing right on top of that first line. So this time what happens is when everything is said and done, they are the same line, which means they have the same slope and the same y-intercept. Everything about them has to be the same. And here, if we think about this as our solution is where these lines intersect, they're intersecting everywhere at every single point on our line. And so we call this infinitely many solutions because there are infinitely many points along our line. And so we may not necessarily talk about what the solutions are, but we could. They're all the points along this line. But we say, hey, there's a lot of them, like so many that we can't count them. And just so you know, that's not the same as saying that our answer is infinity, like using the infinity symbol or something like that. Whenever we write our answer for this, we want to write out that there are infinitely many solutions and not just try to shortcut it by abbreviating it. So in the rest of this video, we're going to work out using graphing, substitution, and elimination and see what happens when these special cases occur. So all of these are going to be special cases in this video, either no solution or infinitely many solutions. But just know that usually in a section like this, where you're doing this, not all the problems will end up being special cases. They'll mix in some regular problems as well. We're just going to look at special cases because we've already looked at the other ones. So it tells me in example 1 to use the substitution method. If it didn't, I would be able to use whatever method I want. So the substitution method here, I would need to pick a variable to solve for. The best one to solve for is this y, because it doesn't have a number in front. So that means I would add 8x to both sides and get y equals 8x minus 7. I'm going to take this 8x minus 7, which is what y equals, and put it in my other equation right here where y is. So that I get negative 16x plus 2 times 8x minus 7 equals negative 8. I will distribute. And here's what happens whenever we have a special case, is negative 16x plus 16x gives us 0x. In other words, they cancel each other out. Negative 14 now equals negative 8. And we can stop here, or you could keep going and like add 14 to both sides and get 0 equals 6. Or add 8 to both sides, and that would give us negative 6 equals 0. Doesn't matter which of these three places we stop at, and we don't need all three. What matters is that after our x's are not the same number. And so when they are not the same number, then our answer is no solution. Because basically this means that they're because of the fact that those numbers don't match. What's cool about special cases is that it actually helps us do less work, because once our variables cancel out, we just stop and say either no solution or infinitely many solutions, depending on what it is. So we don't have to go back and try to plug in to find something because there isn't anything to find. There is no answer to this problem. Example 2 also asks us to use substitution, and so this time this y right here would be the best place to solve for. And so I'm going to subtract 5x from both sides and get y equals negative 5x plus 16. You can write that the other way around, by the way. You can write 16 minus 5x, and that's fine. This is going to go right here in this other equation. So 10x plus 2 times negative 5 plus 16 equals 32. We're going to distribute. And just like last time, our variables cancel. 10x minus 10x is 0x. But this time we have 32 equals 32, or we could subtract 32 from both sides and get 0 equals 0. Whichever of these two that we get, wherever we decide to stop, what's important here is that we have a true statement. 32 really does equal 32. 0 really does equal 0. Because what we got is true, then our answer is infinitely many solutions. And so this is going to happen with elimination, is that whenever we are working through the problem, our variables will cancel. If it's no solution, we get something that is not true. We get numbers that don't match. And it's infinitely many solutions whenever we do get numbers that match, when we do get a true statement. So let's do this with linear combinations, which is the other way of saying elimination. And let's just check out and see how this works. So if I want to use elimination, it looks like the easiest thing to do is to times the bottom equation by 3, because I want to get, I want to pick either x or y to try to eliminate. If I pick x, I'm trying to get a negative 3 in front of the x in this second equation so that I can cancel them out. So negative 3x minus 6y equals negative 3. I'm going to ignore this middle equation for the time being and add the first one and the one I just came up with. What happens here is this cancels, and this cancels, leaving us with 0 equals 0. Just like when we were doing substitution, 0 equals 0 is true. So we say, oh, that's infinitely many solutions. On example 4, we want to use elimination or linear combinations. We want to multiply so that we can get a negative 9x, but that also gives us negative 9y and negative 15. So this time the x's and y's cancel, leaving us with 0 on the left, but on the right side we're left with negative 6. 0 does not equal negative 6, so we say this is no solution. And at this point you may be starting to notice a pattern here of a way that you can tell kind of going into this just from looking at the problem if you're going to have a special case. And so that the significant thing here on each of these examples is that there is something that we could multiply by for our x's and our y's in common. So like what I mean by that is that multiplying by 3 here got us to negative 9 for both of these. If I look back at example 3, if I multiplied the whole equation by 3, the second one, it gave me the first one. That's how I knew that they were the same line, infinitely many solutions. On this one, we didn't use elimination, but look, if I times the whole second equation by 2, I get the top equation, 10x, 2y, and 32. So they ended up being the same line. On example 1, if I times the top equation by 2, I almost get the exact same thing, except for the numbers. I get negative 16x plus 2y equals negative 14. So that made it be almost the same line, but now when we graph, it might be, depending on the equations they give us, it might be super obvious before you graph it that they are parallel or that they're the same line, but you do need to go ahead and follow through and make sure that you actually show the graph and show why you're saying it is what it is, because it's important that we show our work and are able to prove that what we're doing is true. So to graph this, I need to subtract 2x on this first one, and I get negative y equals negative 2x minus 2. I'm going to divide by negative 1 so that I get rid of the negative in front of y. So y equals positive 2x plus 2. So that starts here, goes up 2 over 1. So we've got this line right here. And then whenever I solve the second one, I probably noticed without even having to write it down that something really similar happens. Except instead of a 2, I've got a 4. So as soon as we see that these are both 2x, so they both have the same slope, that means that it's a special case. Once we see that their y-intercepts are different, then that suggests that this is no solution because they are parallel lines. So, solution. And finally, we'll solve this for y, these for y, and graph them. We subtract x, divide by 2, we get negative 1/2 x plus 3. Here's the first line. And then I'm going to add 3x. Divide by negative 6. And get negative 1/2 x plus 3. So as soon as I wrote the same equation down twice, it's like, okay, well, I know these are the same line. You can try to go over the line again if you want. But basically, we just need to say, hey, this is infinitely many solutions because I have the same exact line. So keep in mind, though, that probably whatever your teacher gives you to work on with this, they shouldn't all end up being special cases. There will probably be some mixed in that give you actual points, so that you have to actually be paying attention to when is it a special case and when is it not. So those are the special types of linear systems that we can have, and how to find them and identify them correctly.